Hi everyone and welcome back to this series of tutorials about the use of WEKA as a machine learning tool for power system asset assessment. And today we'll learn something a bit different than what we did so far. Just as a sort of introduction, uh, the type of feature vectors that we dealt so far are what I call limited input feature vectors, meaning the following. For example, we have a feature vector here, the water, acidity, BDF, and the other types of oil test parameters. And here, when you look that each feature, each element of the feature vector is one number. 3 for the water, 2, 1, and so on and so forth. Same thing for the acidity, the BDV, and all other features. When you look to the second problem, when we try to classify the defects in ceramic insulators, again, we have the feature vector is basically the 60 hertz, 120 hertz, 180 hertz, which are the frequency component of the envelope of the ultrasonic signal. And again, we have for the 60 hertz, we have one number, 120, 180. So the number of the feature vector is very, very limited, and we don't have a problem in dealing with a huge data in the input feature. That's not always the case. Now, for example, when we deal with 1D signals, raw signals, not like the one we did in the in the ultrasonic, which we got the f of t, and it was only 3 components. Now, when we get something like this is an RF signal uh, measured using an RF antenna to detect partial discharge. And this signal is 10,000 points for just one signal. So imagine that I want to, for example, classify, let's say, 2 different types of problems. Let's say corona and surface discharge. Okay. Now, I need, let's say, 100 signals for the corona, 100 signals for the surface discharge. So we need 100 signal, 100 signal. If every signal is 10,000 points, you multiply, you get 1 million data point for the input feature. Okay, so that's a huge, this is a huge input feature and will make the computational very, very lengthy. Plus, maybe not all parts of the signal is important for the classification. Maybe only certain features in the signal is important to classify the discharges. I don't need to enter the raw data as an input feature. And this will lead us to have something very important concept in machine learning that we didn't apply so far, which is feature extraction. So when we have a huge data like this one, this is, we call it 1D signal, okay? Or maybe that we'll do that in the future when we have 2D signal. 2D signal means an image. Okay, so when we deal with 1D signal or 2D signal, we have a huge data set. And if I try to feed this data set as it is, then I will have a huge input feature vector. Now, this approach is applicable for deep learning. And if you never heard this word, this is a very important new trend in machine learning, the deep learning. You can feed the raw data as it is, and deep learning classifier will be able to extract the feature by themselves. But the drawback of the deep learning is that you have to feed tens and thousands or tens of thousands of signals so that it can construct the machine learning algorithm. We're not talking about deep learning in this set of tutorials. We are talking about machine learning, the classical machine learning, where you have to deal with a limited number of features. Okay, so how extract the features? You can classify for 1D signal. There are 2 main classes of features can be extracted. The first one is the statistical features. So you can take the signal, this signal as it is, and then extract from it certain features like the standard one, for example, the variance, the standard deviation, but also you can take the kurtosis, okay, and the skewness, okay. So the kurtosis is a measure of the sharpness. How sharp is the distribution of the data? So for example, here we looked at the kurtosis of signal A is larger than B, larger than C, and see here that as the kurtosis value increases, the distribution become more and more sharper and sharper. And also the skewness, it measures the asymmetry of any data distribution with respect to the normal distribution. Is it skewed to the right or skewed to the left? As you see here, this is the skewness here is greater than 0. When skewed this way, it is less than 0. So the skewness can be either positive or negative, and you can see here, because this is to the power of 4, the kurtosis is always a positive number, but this is to the power of 3, so this could be skewed to the right or skewed to the left. And you look here to the formula, they are very similar. The kurtosis, the only difference, you are taking the difference between the signal and its mean, okay, divide by n, the number of signals, and the standard deviation. But the only difference here, you are dealing to the power of 4, the skewness to the power of 3. So this is statistical features, and this is what we'll be using in this exercise. Also, you can deal with spectral features. So you can retransform, or more advanced, the wavelet transform. Now, hopefully in the future, we will come and talk about these two features, which is the frequency content of the signal. Here, the Fourier transform for the signal, you can see here in the x-axis, this is the frequency. And you have here many signal components at different frequencies, okay. And here the wavelet, basically the wavelet is different than the Fourier transform, where you have the time frequency information. I don't need to go in details in this, because we can have like a different tutorial talking about the wavelet and what is basically it means, and how we can use it in our classification problem. Now, the Fourier transform will lead to another problem, because you will have too many frequency components. Unlike the statistical features, we will have like few ones, 3, 4, that's it from the signal. But here for the Fourier transform, you will have too many signal, too many components, and then you have to select. Then we have to go to another issue, which is feature selection, which is a very important topic in machine learning, and we'll talk about that in near future, how to select the important features. So far, we are using the whole feature vector we have. Is all the components are important, equally important? Is there any feature that are redundant, means I can take it out without affecting the accuracy? This is a very important issue, and I will come to it soon. The wavelet transform, on the other hand, you can have less number of features, but as I said, this is another topic. So what is our problem? We will use an RF antenna. This is the antenna, to classify 3 different problems in outdoor insulators, namely the corona. We did that in the ultrasonic sensor. Surface crack, again, we did that. And here, internal void. So we have here an internal void inside the cap and pin insulator. Now, if you remember, in the ultrasonic, the third class was not internal void. The third class was wetting surface. Okay. Now, the wetting surface cannot be detected by the RF antenna. Why is that? The wetting surface will lead to dry band arcing. A dry band arcing is a very low frequency component. We are talking about multiple of here in Canada 160 hertz, like 180 hertz, maybe 300 hertz. Okay, but in so the ultrasonic sensor, since it detects sound, it can detect that. However, the RF antenna, the bandwidth of this antenna is between 1 to 2 gigahertz. So if we are talking about a phenomena in few hundreds of hertz, it cannot be seen by the antenna. It cannot detect the low frequency phenomena. And this is one of the drawback of the RF antenna. It cannot detect low frequency like the surface with discharge, unless the surface discharge can produce a sort of surface corona. And we'll talk about that again in a different video, that you could have high frequency coming from the wetting surface, but that's not the dry band arcing on the surface. And there's a difference between the surface corona and the dry band arcing, and I will dedicate one video in the playlist of Outdoor Insulator Corner to explain the difference between the two. Okay, so this is a drawback of the RF antenna. However, we have here a different problem, which is the internal voids, and we did not use the ultrasonic sensor. Why? Because once you have an internal discharge, remember this discharge has to be going outside, propagated outside. Now it will propagate in the form of an RF signal and in the form of ultrasonic sensor. So these two phenomena happen at the same time. Now, the ultrasonic sensor has or the signal has a problem, that most of its energy will be absorbed by the solid dielectric. So you will have a very weak signal. I didn't try yet, to be honest, to measure the internal discharge using an ultrasonic sensor, but it will be very, very challenging. And I'm planning to do that with a new sensor that we just purchased. However, the RF antenna, the signal can propagate, and it will not be attenuated with this dielectric, solid dielectric material. Very minimum attenuation will happen to the signal. So this is why we can use the ultrasonic sensor, and this is a clear advantage of the sensor. So it's very important to understand the capability of your sensor before you start doing certain measurement. Okay, so now this is a typical corona signal that comes from the sharp electrode or the sharp wire around the cabin bin insulator. This is a typical signal from the surface crack, a typical signal from the internal void, and you can see here that the signals are different even from the time domain. Now we did extracted the two features, which is the kurtosis and the skewness. And these some typical values for the corona, for the surface crack, and for the internal void. These are some typical values of the skewness and the kurtosis. Now let's go to our exercise, and let's go to WEKA, and we will try to see, okay, what is the classification accuracy we can get using WEKA. And we will do again the same thing what we did all the time. We will try to apply the different classifiers, basically ANN, KNN, SVM, and G4048. Now, there is nothing special about these classifiers other than that these classifiers are the way they perform is different from one to another. ANN is different than SVM, is if different than KNN, is different than the G48, which is like a tree type of classifier. Okay, so for this reason, we try those for different classifier, but there is no reason to not to try other classifiers. So let's do our regular way. So we will choose Explorer as usual, and then we will open the file. Okay, select our file. Our files is here. Okay, so we'll have here the RF signal. Choose the CSV file. Okay, there's nothing new here. This is everything, and this is our types of discharges file. Okay, so we have here the skewness. This is the minimum, maximum, mean, standard deviation of the skewness, and this is for the kurtosis. Okay, as I see here, the kurtosis is always positive. The skewness can be negative or can be positive, and these are the three discharge types. You have here 20, 20, and 10 signals. So we have very, very less number of signals. So this is actually, this exercise is done just for demonstration to you that I can extract certain feature from a huge data set, which is the RF signal, which will make the classification much easier. And also there is some even unbalance in the data. Now we understand these issues, but this is just for the sake of the demonstration. So let's choose our favorite classifiers. So we'll choose always we start with the ANN. We'll choose the number of hidden layers to be 2. Let's start with 1, actually. Let's do it as 1 first and see what we'll get. And start. So here we get 80%. So when you look here, for the corona and the surface crack, we have high accuracy. This is corona is 85% and the surface is 100%, but the internal void is 30%, very, very low, because we know, because the list number of, I mean, the whole number of data points is small, especially for the last class. If we come here and change this into 2, okay, and start. Okay, we get 84%, and now we'll see much better for the internal void. We get 70% and a bit reduction of the other 2 classes for the corona and for the surface crack. Okay, now we can try other classifiers. If we try the, I will show you all the results, but just here playing with the classifier. So this is the KNN1. So we get 78%. Okay, and this is the values. If we try to increase the number of distances, let's say to 3, okay, this was 78%. Start, it went down, and this is the few cases when you increase the number of distances, it went down. Let's try to go to 5, see if there's any improvement or further reduction. Start, we go back to 78%. So far 84% is the highest classification accuracy we got so far from all the classifiers. And here is the summary of the results that we got. So this is the ANN 84%, KNN5 78, SVM is the lowest, was 74%, and G48 is 78%. Okay, the classification accuracy is not really the issue actually of this exercise. The issue here is how to extract limited number of features when you have a very large feature vector that will make it very hard to make a regular machine learning classifier. As I said, yes, when you have a huge data long signal like this, you can feed them directly to what we call the deep learning, but that's not the point here. The deep learning has this big advantages. However, the deep learning main disadvantage of it, you have to have tens and thousands of signals so that you can train a good algorithm. Okay, thank you for joining me, and looking forward to meet you in the future.